Good afternoon and welcome to Hand-Wavy Chemistry, where we do not delight in the details, but rather bask in the big picture. Today, we're going to be discussing how this shelving unit can be used to explain the Bohr model of the atom. But before we get to that, I want to talk about Bunsen burners. When we think of fire, we often think of this glowy, red-yellow hotness. However, most of the time, that yellow flame that we see is there because of impurities. There is incomplete combustion, meaning that soot and other material is going up with the flame, getting hot and glowing yellow. This is a problem for researchers. Firstly, it prevents the flame from ever reaching its maximum possible temperature. Second of all, those impurities and soot could be deposited on glassware or other important pieces of instrumentation. And finally, if you want to be able to examine light that's coming out from things being heated by the flame, that yellow is going to obstruct it as well. Now, the Bunsen burner was an important invention because it produced an almost colorless flame, which meant that if a researcher were to place a material into it, any color that got observed would be due to the material that was placed. And as they looked at different elements, different materials, different compounds being heated, they started to notice that there were specific colors associated with different elements. They could even see this when they looked at light coming from the sun. This is how helium was discovered. During a solar eclipse, they analyzed the spectrum coming from the sun, and they recognized that there was an element in the sun that they had not yet discovered. So they named it helium after the sun. The Rutherford model of the atom has no way to explain why it is that these lines, these spectral lines, appear. It also has no way to explain why it is that the electrons don't just spiral down into the nucleus. There's nothing that really stabilizes them in their orbits. This is when Niels Bohr comes in. The start of the 20th century, there's this new idea going around that perhaps energy and the subatomic world is quantized. Things have to exist in discrete steps. Just like we can't have half a proton or half an electron, there could be a minimum-sized packet of energy. So what Bohr said or thought was, if we were to take the Rutherford model of the atom, we've got electrons in orbits as though it's a solar system, a planetary type model. But rather than saying they can be anywhere, we put them into precise, discrete locations, like shelves. The electron could be on this shelf, it could be up on this shelf, but it couldn't be halfway between the shelves. It would have to be here or here. Such steps would prevent the electron from being able to spiral down into the nucleus because it has to move in discrete jumps. This model also did a fantastic job of explaining the spectral lines for hydrogen. These lines have been able to be mathematically modeled and predicted long before Bohr and Rutherford were coming up with their models for the atom. However, no one could explain why. So what Bohr said was there is an exact energy difference between each of these levels. So to move the electron up, you have to put in exactly this amount of energy. If you put in too much or too little, it won't move. Also, if an electron is on a higher energy level and it were to drop down, This model predicts that it would release energy, it would release a photon of light equal to this gap. And Bohr was able to describe the hydrogen atom's spectral lines. He could also describe the spectral line to something like ionized helium and how its electron would move up and down between different levels. About 1 year after Bohr published his model of the atom, the Frank Hertz experiment was conducted. Now, this experiment didn't involve photons. It wasn't shooting light at atoms. It was firing electrons. These electrons were fired at a thin mercury vapor, and they could change the amount of energy that the electrons have. However, what they found was when the electrons traveled through the mercury vapor, they always lost exactly the same amount of energy. This agreed with the idea that the energy states within an atom are quantized, because always the same amount of energy was being lost, therefore always the same amount was being absorbed. So the electron was always jumping by the same amount. However, the Bohr model still has problems. Firstly, while it beautifully predicts the spectral lines for hydrogen, ionized helium, and doubly ionized lithium, it fails to predict the spectral lines for atoms that actually have more than one electron. It also makes some predictions about certain characteristics and energy levels that experimentally we know are wrong. These issues will later be addressed by the modern quantum model of the atom, which involves sublevels, shelves within shelves. But that is a story for another day. If you have enjoyed this video, please make sure to click like and subscribe and share it with your friends. And if there's anything you'd like to say about what you've just seen, or suggest as a topic for a future video, please put it in the description below. Thank you, and I hope you have a wonderful rest of your day.